Okay, here we are. We're talking about our waves now. So last video we were discussing the simple harmonic motion. So we looked at a pendulum swinging back and forth. And I know that it kind of got cut off a little bit at the end of that video. And so what I was talking about was amplitude. And amplitude represents the amount of energy that I gave a wave or gave that pendulum. And so if I give it more energy by pulling it back farther, I've increased its amplitude. I've given it more potential energy at that point. When I let go of it, it'll actually swing forward, and then it'll have greater kinetic energy as it passes through that bottom point, and it'll get over here. Now, amplitude has nothing to do, again, with the period of the pendulum. So in other words, it's going to take the same amount of time to go across and back as it would if I was doing it from here and across and back. It's just that it goes at a different rate. Okay, it has different amount of energy, different potential energy, different kinetic energy. So that's all that it matters when we're starting to talk about amplitudes. We'll carry that forward into this section too when we talk about our waves and wave types and where an amplitude would be. Okay, so let's get started here. We are looking at different types of waves, and there's kind of two broad categories of waves. One is mechanical waves, and that's what we're going to focus on first, is mechanical waves. The other types of waves are called electromagnetic waves. And electromagnetic waves are things like light and infrared and microwave and X-rays. And you probably spent some time talking about them in a chemistry class. So we looked at electromagnetic waves in a chemistry sense when we were talking about electrons and emitting photons and all that good stuff. Mechanical waves, different category of wave. Mechanical waves, the big difference here is that they require a medium, okay, where electromagnetic waves can pass through a vacuum, okay. Now, when we say it requires a medium is something that is a carrier for the wave. It has the ability to carry the energy that wave has, okay. So a wave is nothing more than a way to carry energy, or it's a form of energy that's passing through something. The medium then represents the matter, okay? Something like air, okay? Sound travels through air because the air molecules are the matter that's actually able to take and absorb that energy and transfer it from one air molecule to another. So those are the types of things that we see when we look at mechanical waves. Now, I'm going to be using some terminology here, and there's a lot more vocabulary type things when we talk about waves and wave motion and that. And so when I look at a mechanical wave, I can talk from a sense of a pulse versus something that's periodic. Okay. Now a wave pulse is just when I take, like, for instance, a slinky. So my slinky could be the medium that I'm going to try to transfer a wave through. And if I did a pulse, I just whip back and forth once and let that wave create this pulse pattern. Okay. Now that pulse then would be traveling this direction. Okay. The matter doesn't travel that direction. It's the energy, the wave energy that travels that direction. Now that's a little different than if we said, let's send something that's a little more periodic. Okay, periodic draws us back into that whole concept of what we were talking about with a pendulum. Where a pendulum swings back and forth and back and forth. And I had everybody do this with their hand, and they went like this, and saw that we oscillate between a maximum and a minimum and a maximum and minimum. And then if we did this where we went maximum and a minimum and then a maximum and a minimum, we're actually creating that wave pattern, okay? And so here's where I'm getting a periodic pattern, okay? Something that looks a lot more like a sine curve or a cosine curve from a math class, okay? So that's taking the wave and moving it back and forth. Now that's kind of where we create various wave patterns, and of our mechanical waves we have kind of several types of waves, and it's really about looking at how does the matter move relative to the wave energy, okay? And so here's the first one. We're looking at a transverse wave. Transverse waves are waves in which the matter, the medium, is vibrating back and forth this way, but the wave energy is traveling this way. So we see this up and down, and it's kind of what we call a perpendicular motion to the movement of the matter. Okay, so transverse wave. This is my example of a transverse wave. Now, when we start talking about waves, each of these waves have various parts to them. And when we look at transverse waves, we always look at it and say that we have kind of this area up here that we like to call a crest. And we have this area down here which we like to call a trough. Okay? Crests and trough are kind of our highs and lows on a transverse wave. We also like to measure the amount of distance that a wave travels, and so we have to know what represents an actual wavelength. You can see in my image here, it's a trough to a trough, and that represents a wavelength. But we could also go from a crest to a crest, or any corresponding point to any corresponding point, and they're all going to be the same wavelength, okay, same amount of distance. Okay, wavelength is a distance measured in meters. And that's an important thing to know, because we always like to know about lengths, and then we like to know about times, and that gets us into speed, which is kind of coming up here. Now, the amplitude then is usually based on, if we drew in a center line, okay, the amplitude would represent the distance that we are from like the normal place. Okay, so that's how we kind of look at the amplitude. And again, bigger the amplitude, the more energy we have. We'd still have maybe the same wavelength, we'd still have the same amount of time, it's just carrying more energy. Okay, and so that's what we talk about when we talk about amplitudes. The next type of a wave is a longitudinal wave, and longitudinal waves are ones in which the matter vibrates this direction. So in other words, I have a piece of matter here that pushes on this one, which pushes on this one, which pushes on this one, and the matter just kind of moves back and forth. So we get these things that look like compressions. So we get a compression in here, okay? And then we get this expansion in between here. And really the expansion by vocabulary sense is called a rarefaction. And that's kind of our analogy or our similar points relative to like a crest and a trough on a transverse wave. So in other words, compressions are like crests and rarefactions are like troughs, and so that's how we kind of measure it. And again, if we're measuring a wavelength, we measure a wavelength the same way. We measure it from corresponding point to corresponding point, or corresponding point to corresponding point, and that's how we measure wavelengths. Okay. The last, okay, that was the matter going this way. We've got the matter going this way. Now, when we look at like a surface wave, and a surface wave is a lot more like what we would see on a lake or an ocean here, or a lake on Minnesota, okay, where the wave matter seems to be going like this. It's like it does a little like kind of circular motion. So in other words, my matter point, if I were to say like have a little rubber ducky attached to or in the water, we would see that it goes up and down, but it kind of goes forward a little bit and backwards a little bit. So a surface wave is kind of a combination of a transverse wave and a longitudinal wave kind of combined, okay, where we see kind of more of a circular motion with our matter. Okay, of these, the ones that we'll probably talk about the most would be transverse waves and longitudinal waves. We just look at surface waves because, you know, we're always on boats here. So. All right, that's mechanical waves. Now, we just talked a little bit about length, and that's the wavelength, and that we can see speeds. Now, because if we know the times, we can relate to the speeds. Our math is basically this. Wave speed, okay, is the wavelength times the frequency. Now, if you remember, wavelength is measured in something like meters, and frequency is measured in hertz, okay? Hertz is the same thing as a per second. Remember, the definition of a frequency is the number of waves per given time, okay? So it's like 10 cycles per second, okay, or something along that line. And when you take these two values and you multiply them together, you end up with something that's in meters per second. That's exactly what we wanted to get. So this is an example problem of how do we handle doing this. By the way, formula-wise, it would look a little bit like this. So my wave speed equals frequency times wavelength, okay? And if you remember, you probably used the wavelength symbol in a chemistry class, and I know some of you haven't taken chemistry yet, but this is just basically our upside down looking y. It's a Greek symbol. It stands for lambda, and that represents wavelength. Okay, so if I look at this again, I have a piano string tuned to middle C. It has a frequency of 264 hertz, and we know that the speed of sound in air is 343 meters per second. So we're now looking for the wavelength of this sound. All right. So in other words, they gave me the speed, 343 meters per second. They gave me the frequency, 264 hertz, and we're looking for the wavelength. Okay, so it's pretty straightforward. All we have to do is divide by 264 hertz, divide by 264 hertz, and we would then end up with a wavelength. Let me grab my calculator. And so our 343 divided by 264 is like 1.3 meters. All right. Pretty straightforward problem, okay? And they're not very hard when we look at something like that. Now the other option is that you may see a little more difficulty because they may not give you the frequency, but remember there's a relationship between frequency and period. So maybe they gave you the amount of time that it takes for, say, one wave to pass. And the frequency, of course, is the reciprocal of the period. So that's just another way to look at it. We've already kind of talked about that as well. All right, so let's go to the next one. We start to look at wave interactions. So now waves can kind of interact with other things. So like a wall or like other medium. Okay, so maybe a wave transfers from, say, water to air or air into water or something like that. Or maybe we just have two waves that kind of come contacting each other. So if you're out there and you're doing some wakeboarding or kneeboarding or tubing in the summertime, you'll make a loop with your boat, and all of a sudden that wave from the wake off of here comes against that one, and you get these big, huge, giant wakes, or these big, huge, giant troughs. And what we're looking at then is wave interaction. Okay, so this is our superposition. So now there's kind of two things that happen when we look at superposition. And all we mean by the word superposition is that these waves are going to come together with each other, and they're going to be an additive feature. So in other words, if I look at, here's a wave pulse traveling this direction, and I have another wave pulse traveling in this direction, these two wave pulses will pass through each other. Okay, so they'll pass through. So in other words, if I made, let's make this one a little bigger. So this is a big wave coming this way, and this is a little wave coming this way. The big wave will still come through and end up over here as a big wave, and this one will be a little wave. Okay, so in other words, this one's still traveling this way, and this one's still traveling this way. The question is, what happens in the middle? Okay, what happens when the two come together? Now, because both of my waves are on the same side, they're going to add together, and I'm going to get like this huge wave pattern, and we call that then constructive interference. Okay, constructive interference. It's when two waves combine together and we see an addition of those two waves. Now we can also have what we call a destructive interference. Okay, and a destructive interference would be if I said, let's pass two waves, and so here's a wave pulse coming this way, and here's a wave pulse coming this way, but this pulse is on the opposite side. So in other words, now they have opposite energies. Okay, one has a wave energy that's kind of, we could say, positive energy, the other one has a negative energy, and as they combine together, they kind of start to cancel each other out. And this is called destructive interference. And so we actually see the two waves kind of canceling each other out. The last thing that I want to kind of talk about in the next 30 seconds here is reflection. Okay, and when we see, say, like a wave pulse coming at a wall, okay, so I've got a string, it's connected there, I'm sending my wave pulse there. As it comes and it hits this wall, it actually will flip itself over, and it'll come back on the opposite side. And it forces itself to do that because of the reflection properties. And we'll see that in a lot of different situations. So I'm almost out of time, and so I'll see you next